Welcome to this talk. I'm Chen. I'm very happy to introduce our paper, Forerunner, Constraint-based Speculative Execution for Ethereum. Speculative execution has been successfully applied to many systems. This idea can be employed whenever we have a piece of code which we know will be executed later. And the input to the code, which determines its execution results, will only be fully known when it is time for the execution to happen. By making a prediction on the input, we can pre-execute the code on spare or idle resources. If the prediction is later found to be correct, the actual execution can be skipped with the pre-execution results returned, which achieves acceleration for the actual execution. However, this does not work and incurs the checking slowdown when the prediction turns out to be wrong. Traditionally, this is not a big problem. It is because that speculative execution has been mostly applied to single future environments, in which simply betting on the most likely future is a feasible strategy. In this work, we consider the problem of many future speculative execution. This is motivated by the opportunity and challenge in the transaction processing of the Ethereum blockchain. As a programmable blockchain, Ethereum transactions are specified in Turing-complete smart contracts, whose non-trivial execution is the bottleneck of the blockchain. Ethereum operates in a dissemination, consensus, and execution model, or briefly, a dice model. In this model, transactions are first disseminated through broadcast, then accepted into a chain of blocks by a decentralized consensus process, and only after that, executed sequentially by all Ethereum nodes. While the dissemination to execution window creates a natural opportunity for speculative execution due to the decentralized dissemination and consensus process, there are many possible orders or ways a transaction can be accepted into the blockchain, leading to many different possible future executions. Usually, none of these futures has a dominant probability. It means that as long as we only make a single prediction for each transaction, no matter which future we bet on each time, the accuracy will not be very high. This is a many future situation that is challenging for the traditional single future speculative execution technique. Intuitively, we solve the many future challenge by finding a way to allow one or very few pre-executions to cover a large percentage of the possibility space of the futures. This essentially requires cross-future acceleration. It means that we try to leverage the pre-execution in one predicted future to accelerate the execution not only in that specific future, but also in other futures. In that sense, traditional speculative execution does only same future acceleration. Of course, we cannot expect that the acceleration speedup achieved in a cross-future fashion will be as high as in the same future fashion. However, it is reasonable to expect that the more similar the predicted future to the actual one, the higher the acceleration. Once we decide to do multiple pre-executions, each in a distinct speculative future, we can imagine another kind of cross-future acceleration, which in some sense is the dual of the one-to-many idea just described. It is the ability to make use of as many pre-executions as available to better accelerate the one true future that actually happens. The intuition of this many-to-one idea is to break the pre-executions apart and reassemble the parts together to approximate the actual execution as closely as possible. The goal is to use the increased similarity to achieve higher acceleration. Ideally, it should allow us to combinatorially compose a large number of pre-executions out of a few actually pre-executed ones, increasing the likelihood that we hit on the actual future or something closer to it. To achieve cross-future acceleration, we need to identify inherent similarity that connects the futures in a way that the computation done in one future can be used to accelerate the execution in another. Our key insight is to view each possible future execution as an instruction trace and employ a structural equivalence of the traces to achieve cross-future acceleration. The structural equivalence we propose is named CD-Equivalence. Two executions are CD-equivalent if and only if their traces have identical control flow and data flow. It means that the two execute exactly the same sequence of instructions, and the cross-instruction data dependencies are also exactly the same. The notion of CD-equivalence is an equivalence relation, which partitions all the possible future executions into equivalence classes. By definition, all the executions in a class follow the same CD-equivalent instruction trace. It means that if we can somehow turn any of the traces into an executable program, it can produce identical results as the original transaction code in all the futures of the same class. A very important and useful property of such a trace program is that, being specific to a CD-Equivalence class, it is essentially a fixed sequence of unrolled and inline instructions with fully determined data dependencies, which makes it highly optimizable. It means that we can record the trace of the pre-execution in a speculated future and aggressively specialize the trace into a much shorter and more efficient faster pass program for a whole class of futures. To make sure such a faster pass is only used in futures of the right class, a set of CD-equivalence constraints are checked before its execution. From another point of view, an equivalence class is uniquely defined or characterized by such a set of constraints. The constraint-based faster pass scheme is our core mechanism to achieve cross-future acceleration, onto which many more innovations are added to significantly improve the efficiency. Another very important reason we choose CD-equivalence is based on a key observation about Ethereum's real workload. It is common that many different futures of an Ethereum transaction have CD-equivalent executions. A concrete example is shown in our paper to explain the intuition behind. This observation means that the chance that the actual execution is CD equivalent to one of the pre-executions can thus be accelerated is high. The design for our solution is a novel multi-trace speculative program specialization technique enhanced by a new form of memoization. It traces pre-executions and specializes the traces to an accelerated program or an AP, which is constraint checking code followed by faster pass program. Then it adds shortcuts to the AP code, which can further skip segments of AP execution based on values remembered in pre-executions. Here are the highlights of our design. The specialized AP code is much shorter than the original trace. On average, its length is less than 1/10 of the original trace. A key innovation in the specialization process is to retarget specialized AP code to a hugely simplified, register-only and control flow-free VM, which has much higher execution efficiency than the original VM that leads to support the full semantics of the original code. It means that the much shorter AP code also runs in a more efficient VM. The AP execution is rollback-free. AP won't make any externally visible changes until it is sure that the future can be accelerated by its fast passes. It means that, upon speculation failure, we can immediately fall back to the original code without reverting anything. We have an innovative way to do merged constraint checking for APs that cover multiple equivalence classes with multiple fast passes. This ensures that the constraint checking cost does not grow with the number of classes covered. The shortcuts added are very flexible and powerful. It can skip different segments of an AP execution independently based on the values remembered in different pre-executed futures. This is how we achieve the many-to-one cross-acceleration. In the evaluation, we observe that more than 80% of the AP code can be skipped by the shortcuts. In the best case of a perfect prediction made, shortcuts can skip all the computation instructions of an AP, which is almost as efficient as the traditional approach would perform. This makes our approach a generalization of the traditional speculative execution. Last but not the least, the specialization and the memoization process is designed to run very fast so that it can generate APs in time before the actual execution needs to happen. To validate our approach, we implement Forerunner as a transaction accelerator for an Ethereum node and measure the speedups achieved. The implementation works reliably in a real Ethereum node and can correctly handle all the real-world Ethereum transactions and smart contract code. The highlight of our evaluation is that it is conducted in live Ethereum nodes on the live traffic of the blockchain as they happen in real time. This exposes our approach to the real-world code and data, real-world uncertainties of futures, and the real-world time budget for pre-execution and other pre-processing, which is very important for understanding the real effectiveness of a speculative execution technique. To achieve any speedup, our technique needs to finish everything from prediction to specialization and memoization correctly and fast enough in a live system. Our main evaluation runs continuously for 10 days and includes results achieved on 13 million transactions. The average speedup achieved over all these transactions is 6.1. There are 5% of the transactions that were not heard by our nodes during the dissemination phase. Thus, there are no chance to do pre-execution for them in the live evaluation. If these unheard transactions are excluded from the calculation, The effective average speedup achieved by our approach is 8.4. In contrast, the traditional approach can only achieve a speedup of 2 on the same workload, as its single future method fails on half of the workloads due to their many future nature. Our approach can accelerate almost all of these many future transactions. In total, we can accelerate more than 98% of the workload. In this paper, we introduce a novel constraint-based speculative execution approach. This approach is intellectually intriguing because it is the first many-future speculative execution technique, which generalizes how pre-executions can be leveraged to accelerate the actual execution. We propose an implementation in Ethereum and conduct the evaluation on the blockchain's live traffic. Our results show that such a generalized construction can be very profitable in a real system. This accelerated execution capability can be used to increase Ethereum's throughput in its foundational layer. Our code and data are publicly available, and our results are reproducible as verified in the artifact evaluation. That's all. Thanks for your attention. If you are interested, please have a look at our paper for more details and results.